Hi everybody, welcome back. Today what we're going to do is we are going to kick off the week with a little radicals review. So we're going to go over everything that we've learned about radicals so far, and then tomorrow and Wednesday you guys are going to be working on a quizzes assignment regarding everything that we've learned about radicals. All right, so let's get started. The first question asks us to consider the set of numbers: square root of 2, square root of 10, and square root of 23. Is this group of numbers rational or irrational? And how do you know? So rational numbers are integers, so positive or negative whole numbers and 0. And they're also decimals that end or terminate or repeat. Now rational numbers are decimals that do not end and do not repeat. So if I plug in the square root of 2 into my calculator, now if you're using a TI-30 scientific calculator, if you hit the second key and x squared, so you see in light blue above the x squared, you see that square root sign. So if you hit second x squared, you'll see the square root symbol come up on your screen. Type in a 2, close the parentheses and hit enter. You'll see that there's a really long decimal that doesn't end and it doesn't repeat. So the square root of 2 is an irrational number. And I'm not going to write out the number, I'm just saying if it's rational or irrational. How about the square root of 10? So let's do the same thing for the square root of 10. So if I take the square root of 10, I once again end up with an irrational number. It's a decimal that doesn't end and doesn't repeat. Yes, I know you see the 2, 2, and then the 7, 7, and 6, 6, but notice how it's not the same either pattern of numbers or same number repeating over and over every time. So when we talk about repeat, we're talking about either the same number repeating over and over or the same pattern of numbers repeating over and over again. So in this case, we don't have either. So irrational. Last but not least, if I plug in the square root of 23, I get 4.795831523. Again, that is a number or a decimal that doesn't end and doesn't repeat, so this is irrational as well. So this particular set of numbers is irrational because they are decimals that do not end or repeat. Okay? So keeping in mind irrational numbers, let's take a look at question 2. Which of the following results in an irrational number? So we're looking for a number that is a decimal, which doesn't end or repeat. So if I take the square root of 25, so again, going to my calculator, second x squared, 25, close the parentheses, enter, I get 5. So I get a nice whole number, no decimal at all, and the reason for that is because 25 is a perfect square. So number 1, I'm going to cross out because that is not an irrational number. It ends up being rational. If I look at number 2, and I actually do the subtraction here, so 4 minus the square root of 9. So I'm just going to really quickly check to see what the square root of 9 is, and when I type that in, I get 3. So 9 is another perfect square because 3 times 3 is 9. And now if I simplify this a little bit, 4 minus 3 gives me 1. So 1 is a whole number. It is not a decimal that doesn't end or doesn't repeat. So that is a rational number. Looking at number 3, 7 divided by 2. So 7 over 2 gives me 3.5. Well, 3.5 is a decimal, and it ends, it terminates, 0.5, and it's all done. So therefore, this is not an irrational number, it's a rational number. Now let's take a look at 3 plus root 6. So if I take the square root of 6, I just want to see what I get. Oh goodness, I get a really long decimal, no repeating, it doesn't end. So the square root of 6 is an irrational number. Let's say I add 3 to that, and I still have an irrational number, 5.449489743, and it could keep going, but my calculator says it stops because there's no more room on the screen. So this produces, and I'll write down what I'm looking at here, 5.449489743. So a decimal that doesn't end and doesn't repeat. Here is our irrational number. All right, let's move on to square roots. So we're going to evaluate the following square roots, and then we're going to round any answers to the nearest thousandth if necessary. Okay, so evaluate means we want to find out the value of these numbers when the square root is actually taken. So for example, if I take the square root of 32, I'm going to go to my calculator, I'm going to hit second, x squared, 32, close the parentheses, enter, and I see I get a really long decimal. It doesn't end, it doesn't repeat. So the square root of 32 is actually an irrational number. So to evaluate it, I'm going to say the square root of 32 is approximately, rounding to the nearest thousandth, so that's 3 decimal places, 5.657. So 5.657 is the approximate value of the square root of 32. Let's do the same thing for the square root of 98. So second, x squared button, 98, close the parentheses. Yep, once again I come up with a decimal that doesn't end, it doesn't repeat, but I'm going to round to the nearest thousandth here, and I get approximately 9.899. So the approximate value of the square root of 98 is 9.899. Let's look at the square root of 75, same thing. This is another decimal that doesn't end or repeat. So I'm going to say the approximate value here, rounding to 3 decimal places, is 8.660. All right, so now we're going to do some multiplying and adding and subtracting, and we're just going to evaluate what we get. So the square root of 49, okay, square root of 49. Now I'm not sure if some of you remember this number, but 49 is a perfect square. When I take the square root of it, I get 7, because 7 times 7 is 49. How about the square root of 121? All right, so same thing, plug that into your calculator, and I get 11. So both of these values were actually perfect squares. 49 and a 121 were perfect squares. Now multiplying 7 times 11, I get 77. Looking at E, negative 2/3. Remember, this means negative 2/3 times the square root of 81. 81 is a perfect square. What two numbers multiplied together give us 81 that are the same? 9. 9 times 9 is 81. And if you don't memorize that, that's okay. You have your calculator to help you out. So negative 2/3 times 9. Now I'm going to turn 9 into a fraction just to make this multiplication a little easier. 3 goes into 9 3 times. And when simplified, I get negative 6. Last but not least, looking at F, the square root of 36. 36 is a perfect square. What two numbers multiplied together give us 36? 6 and 6. So the square root of 36 is 6 plus 12 minus, okay, the square root of 4. So what two numbers multiplied together give us 4? 2 and 2. So the square root of 4 is just 2. Remember, we're undoing whatever squaring took place when we square root. All right, so now combining everything here from left to right, 6 plus 12 gives us 18, and then 18 minus 2 is 16. So this is how we evaluate square roots. Now let's simplify square roots. So simplify and evaluate are just a little different. In this case, when we simplify, or when we want to write this in simplest radical form, we don't want any decimals. So we're going to pull out any perfect squares that we have, and anything that's not a perfect square is just going to remain underneath our square root. We're not going to do any approximate values for decimals here. So let's take a look at G. G wants us to write the square root of 500 in simplest radical form. So the first thing I'm going to do, and I'm not going to do this for every problem, but I'll at least show you for the first maybe two, and then you guys can do this on your own. But if you can't pick out a perfect square, so remember our goal when we want to write things in simplest radical form is to find a perfect square that's a factor. So what I'm going to do is on the bottom of my page here, I'm going to start listing out some perfect squares. So using the numbers 1 through 20, I'm going to start with the number 1. When I multiply 1 by itself, I get 1. And then 2 times 2 is 4. And 3 times 3 is 9. And 4 times 4 is 16. And 5 times 5 is 25. So these numbers that I'm getting when I multiply 1 times itself and 2 times itself, these are our perfect squares here. So 6 times 6 is 36, then 49, and 64. And if you can memorize these, great. If you can't, that's okay. You have a calculator. Go ahead and say what's 1 times 1, what's 2 times 2, what's 3 times 3, what's 4 times 4, and so on. Okay, let's see, 12, 13 times 13, 14 times 14, 15 times 15, 16, I can only memorize so many. 16 times 16 is 256. 17 times 17 is 289. 18 times 18 is 324. 19 times 19 is 361. You could also say 19 squared, and then 20 squared, or 20 times 20 is 400. Okay, so here are perfect squares that we're looking for as factors to help us simplify these square roots. So if I'm looking at 500, if I start making a little kind of factor tree, so what two numbers multiplied together give me 500? Well, 1 times 500. 2 times 250. Let's see, 3, I don't think we can divide by 3 evenly here. No, we cannot. All right, so 500 divided by 4 gives us 125. So 4 times 125 gives us 500. 500 divided by 5 is 100, so 100 times 5 is 500. So I'm kind of working backwards. I'm actually dividing right now, so I'm taking 500 and let's say divided by 6 to see if 6 could possibly be a factor of 500. So 6 doesn't work out too well, neither does 7. Not 8. We want factors that are not decimals. Let's see, 10 and 50, and I think the last one is 20 and 25. Okay, so now looking at these factors, I'm going to pick out all the perfect squares. So 4 is a perfect square, 100 is a perfect square, and 25 is a perfect square, if you notice our list below. So we want to pick out the largest perfect square when we're trying to simplify square roots. So the largest perfect square I see is 5 and 100. Okay, or 100 is the largest perfect square. So now going back to the simplifying process, I'm going to use the square root of 100 times the square root of 5 to rewrite the square root of 500. Now I'm going to simplify from here. The square root of 100 is 10. The square root of 5 is a really long, yucky decimal, so it is an irrational number. Having said that, I am not going to write a decimal approximation for it. I'm going to leave it as a square root of 5. So now 10 times the square root of 5 can be written as 10 root 5, and we're just going to leave it as that. When we want to simplify in radical form, we don't want any decimal approximations. All right, so looking at H, square root of 80 times a to the power of 56. So let's start. I'm going to break this apart a little bit, and I'm going to take the square root of 80 and put that underneath its own square root. multiplied by the square root of a to the 56th power. So right now I'm just separating all the multiplication that's taking place so that I can work with each term separately to see if I can simplify them each separately, and then we'll multiply them together at the end. So the square root of 80, we could do the same thing that we did off to the side over here. If we would like to make a little factor tree to help us out, we can. So 1 times 80, 2 times 40, 4 times 20. So these are just factors of 80. They're two numbers multiplied together to give us 80. Okay. And now, when I start to pick out all the perfect squares, I see 4 and 16, and I think that's it, using my list below. So which one's bigger, 4 or 16? Well, 16 is. So I'm going to use those factors to help me simplify the square root of 80. So I'm going to rewrite the square root of 80 as the square root of 16 times the square root of 5. What is the square root of 16? Oh, sorry. And you know what? I'm just going to bring down the square root of a to the 56th power. There we go. So what is the square root of 16? The square root of 16 is 4. The square root of 5 is irrational, so I'm going to leave it as the square root of 5. Now the square root of a to the 56th power. Remember, whenever we have a variable raised to a power and we're square rooting it, the trick is to cut the exponent in half. So 56 divided by 2 gives us 28. So this is going to simplify to a to the 28th power. And the reason for that is if we think about our monomial rules, a to the 28th, so don't mind this extra work here, a to the 28th times a to the 28th, we keep the base of a, and according to our rules, we would add the exponents together, which would give us 56. So the same thing being multiplied by itself produces that perfect square. All right, so going back to our problem here, let's combine everything on the outside of the square root. So 4 times a to the 28th gives us 4a to the 28th power, and then the square root of 5 gets tacked on at the end. Okay? All right, I'm not going to make it factor trees anymore. If you want to, you can, but just to make sure I don't make this video too long, I'm just going to tell you the factors that I will be using. And then you guys, if you want, you can stop the video, try and do it yourself, and see if we come up with the same answers. All right, so looking at I, the square root of 117 x to the 30th power. So to simplify this, first thing I'm going to do, I'm going to rewrite this as the square root of 117 times the square root of x to the 30th. I'm just breaking apart some multiplication here. Simplifying each of these individually. Now 117 is not a perfect square, but it does have a factor that's a perfect square, and that is 9. So 9 times 13 is 117. So I'm going to break this apart as the square root of 9 times the square root of 13 times the square root of x to the 30th. Simplifying further, the square root of 9 is 3. The square root of 13 is irrational. We're going to leave that there. And the square root of x to the 30th, cutting 30 in half, I get 15. My final answer, putting together everything on the outside and then leaving this square root at the end. Okay. Looking at J, negative square root 90. So the negative on the outside is kind of the same thing as saying negative 1 times the square root of 90. I'm going to split 90 up into the square root of 9 times the square root of 10. The square root of 9 is 3. The square root of 10 is irrational. And multiplying everything on the outside, I get negative 3 root 10. Looking at K, once again, I'm just going to break everything apart here. All the multiplication I'm going to break apart. So 3 times the square root of 12 times the square root of n to the 10th times the square root of n to the 18th. So this is just me breaking apart all the different multiplication that we have here. So 3 times root 12 I'm going to break apart into the square root of 4 and the square root of 3. The square root of m to the 10th power, cut that exponent in half, we get m to the 5th. times the square root of n to the 18th. If I square root n to the 18th, I get n to the 18 cut in half is 9. Simplifying a little further, the square root of 4 is 2. Square root of 3 is irrational, so I'm going to leave that underneath my square root. And I'm going to bring down times m to the 5th and n to the 9th. I almost started to write another m there. Now I'm going to multiply or bring together everything on the outside of the square root. 3 times 2 is 6. M to the 5th first because m comes before n in the alphabet. N to the 9th. And then root 3. All right, sorry, I'm really squeezing a lot in here. Going on to L, so we're going to take 1/2 times the square root of 32. Now, thinking about factors of 32, the largest factor that's a perfect square is 16. So we're going to break this apart into 16 times 30, or 16 times 2 here. So 1/2 times the square root of 16 gives me 4. The square root of 2 is irrational. We're going to leave that underneath the square root. 1/2 times 4, or in this case 1/2 of 4 is 2. And then the root 2 stays at the end. All right, last but not least, for m, this is the same thing as saying -2 times, and let's see, factors of 288, one of them being a perfect square, 144. And again, use your list below to help you out. Okay, so -2 times the square root of 144 is 12. The square root of 2 is irrational, so you leave that there. And then -2 times 12 is -24. Okay, so here is us simplifying radicals and leaving them in simplest radical form. All right, so let's go on to cube roots. So first thing we're going to do is we're going to evaluate these cube roots. So in order to get a cube root on your scientific calculator, you're going to hit 3, then the second key, and the little up arrow, so you'll notice it's a couple down from the second key, so you're going to stay on that left side. It's the little up arrow, or the caret as they call it, in between the pi and x squared key. So when you hit that, you'll notice there's an x and then a square root. So you're telling the calculator, I'm taking the cube root. I'm putting the 3 in for x. Now we're going to type in the number that we're taking the cube root of, which is 8. So the cube root of 8 is 2. Remember what cube root means. Cube root means what number can I multiply by itself 3 times in order to come up with what's underneath that cube root sign. So 2 times 2 times 2 gives me 8. Okay, so that's why the cube root of 8 is 2. The cube root of -1, so same thing, 3, second, that little caret or up arrow in between pi and x squared, -1 gives us -1, because -1 times -1 times -1 is -1. The cube root of 27, again plugging that into our calculator, we get 3. And the cube root of -2,744, again 3, second, that caret key, -2744, enter, and you get -14. The cube root of 100. Okay, I can tell you right now that 100 is not a perfect cube. So there is no number that we can multiply by itself 3 times to get 100. So we're going to probably have a decimal approximation here. So 3, second, that caret key, 100 gives us approximately, if I'm rounding to the nearest thousandth, I'm going to get approximately 4.642. All right, the cube root of -364, another decimal approximation here, is approximately -7.140. The cube root of 982, again plugging into our calculator, looks like we've got another decimal approximation here, So we get approximately 9.940. Now for h, I'm going to break this apart. I'm going to break the division apart, and I'm going to take the cube root of the numerator divided by the cube root of the denominator. So the cube root of 1 is 1, because 1 times 1 times 1 is 1. The cube root of 64, that one, if you don't know it off the top of your head, 3 second, that little caret key, that little up arrow between pi and x squared, 64. And you get 4. So 4 times 4 times 4 gives us 64. All right. Okay, last but not least, this is what you guys did on Friday of last week. We solved for x. So again, we're trying to find what values of x make these equations true. Now in some of these equations, we're going to have to take the square root. And when that happens, remember, we get two answers, a positive and a negative. And in some of these equations, we might have to take the cube root. Now the cube root, we only end up with one answer. Okay, so let's go ahead and start with number 6. We're going to get all of our cube roots, anything that has a x, I'm sorry, not a cube root, anything that has an x cubed, we're going to get to one side. Anything that's a constant, let's get to the other side. So looking at this equation in number 6, I'm going to bring 2x cubed to the other side using inverse operations. So since 2x cubed is positive, I'm going to subtract 2x cubed from both sides because this is an equality property, so we have to do the same thing on both sides. And I'm left with 2x cubed plus 6 equals 256. Bringing 6 to the other side, I'm going to use the inverse operation of subtraction to undo that addition. And I'm left with 2x cubed equals 250. To undo this multiplication, I'm going to divide, and I get x cubed equal to 125. And to undo a cubed term, I'm going to cube root. Sorry, this looks really funny. There we go. Cube root. So the cube root of 125 gives us 5. So if I were to plug in 5 for x, that would make both sides of my equation equal. It would make this equation true. All right, looking at number 7. So for number 7, we're dealing with x squareds. So I'm going to get all of my x squareds on one side and my constants on the other. I'm going to take this negative 8x squared and I'm actually going to add it to both sides. And when I do that, I get negative 6 plus 8 is 2x squared minus 7 equal to 91. I'm going to bring this minus 7 to the other side using addition. Oops, not 9, but 7. Let's try that again. So I'm going to add 7 to both sides, and when I do that, I'm left with 2x squared equal to 98. Now getting that x squared all by itself, I'm going to undo that multiplication with division, and I'm going to divide by 2 on both sides. And when I do that, I get x squared equal to 49. To undo this squared term, I'm going to square root. Now remember, I'm going to come up with two different answers here. Okay, so the square root of 49 is 7. So when we do this, we get x equals, and remember we're going to say plus or minus 7. And the reason for that is 7 squared, or 7 times 7, is 49, and negative 7 times negative 7 is 49. So there's two different values for x that we can plug in, positive or negative 7. All right, looking at number 8. So number 8, I'm going to get all my cube terms on the same side. In order to not deal with too many negatives, I'm going to subtract 5a cubed from both sides. Since it was positive on the left, in order to bring it to the right, I have to subtract it. Now when I do that, I'm left with 7 equals 3a cubed plus 31. I'm going to bring the 31 over to the other side through subtraction. And when I do that, I get negative 24 equal to 3a cubed. To get the a cubed by itself, I'm going to undo this multiplication with division. And negative 24 divided by 3 is negative 8 equals a cubed. Now to get just a, to undo this cubing that's taking place, I'm going to cube root. And again, it's an equality property. Whatever I do to one side, I have to do to both. So the cube root of negative 8, again, cube root would be 3, second, that little up arrow or that caret key on the left side between pi and x squared, and then we say negative 8 gives us negative 2. So a is negative 2. I can plug in negative 2 and that's going to make my equation true. For number 9, let's start by distributing the 6. That gives me 6x squared plus 30 minus 200 equals 5x squared minus 134. Now seeing this 30 and negative 200 on the same side, I can go ahead and combine those because they're like terms. So this gives me a negative 170. Now I can go ahead and start working across the equal sign. So I'm going to do two things at once here. Hopefully you guys can follow me. I'm going to subtract 5x squared from both sides. And I'm going to add 170 to both sides. So I'm bringing the 170 over the right, and I'm bringing the 5x squared over to the left. I'm just doing it all at once. Okay. So now I'm left with x squared, because 6x squared minus 5x squared is just x squared, or 1x squared. 130, or negative 134 plus 170 gives me a positive 36. All right. Now to get just x, I'm going to have to undo this squaring that's going on, and to undo a squared term, I square root both sides. So these undo each other. And I'm left with x equals, remember whenever we square root, we come up with two answers. The square root of 36 is 6, and I'm going to say plus or minus in front of it. Okay. All right, two more. For number 10, let's once again start by distributing. So negative 3x squared plus 12 equals 5x squared minus 20. Bringing all my squared terms to the same side, I'm going to add 3x squared to both sides so I can undo that negative over there. And that gives me 12 equal to 8x squared minus 20. I'm going to add 20 to the other side to undo the subtraction that's going on. And I get a 32 equals 8x squared. Dividing both sides by 8. I'm going to bring this over here. I get 4 equals x squared. And to undo the square term, I square root both sides. So x equals, the square root of 4 is 2, but don't forget, whenever we square root, we get two answers, so plus or minus 2. All right, last but not least, we've got a lot of combining we can actually do right off the bat with like terms on the same side of the equal sign. So 15 and 2 can be combined. Let's see, the x cubes on that side can be combined, and the constants on the right side can be combined. So a lot of combining before we get started here. So 12x cubed plus, I'm going to combine the 15 and the 2 to get 17, equals, I'm going to combine the x cubes to give 2x cubed, and then the 7 and the 20 give me 27. All right, now we can start working across the equal sign. I'm going to bring this 2x cubed to the other side through subtraction. And that gives me 10x cubed plus 17 equals 27. I'm going to bring the 17 to the right side through subtraction. So 10x cubed equals 10. I'm going to undo the multiplication here with division. And that gives me x cubed equal to 1. And to undo a cubed term, cube root. And the cube root of 1 is 1. All right, so that's it for the radicals review. Make sure you take a look at the quizzes assignment tomorrow and Wednesday and let us know if you guys have any questions.